मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, this is 15th lecture in the series of mechanics of metal forming. Last lecture we discussed the yield, the concept of yield, yielding and flow, and the related yield criteria and related issues. We would continue further from the last lecture. So, as let us recall back where we started determining the constants, particularly the values of the k value from the last equation number 20, where we derived the yield function in terms of the direct stresses, which is sufficient for causing yielding in a material, and we looked into the von Mises yield criteria. As explained, there are two very popular criteria for yielding, one the von Mises and the Tresca. So, let us start with the last that we had, the equation number 20 basically, and then let us, so we started that for the very complex situation of the stresses, and let us apply it for the simple tension as well as pure shear. So, we took the example for the uniaxial tension case, where the tests can, the yield function, the yield criteria equation number 20, if you apply the case for the uniaxial tension, then one can have the relationship like the stresses are only in one direction. So, if you recall it, so we got the equation like the particular equation that we had sigma xx minus thrice k1 square is equal to 0. So, the k1 is the constant that to be determined. So, we can calculate it k1 as 1 by root 3 sigma xx, and that can also be written as 1 by root 3 sigma. Since in pure tension or compression the yield occur when sigma xx reduces the yield stress equal to sigma. So, the k1, which is the constant, was to be determined as 1 by root 3 sigma. So, sigma is your the material property, the flow yielding, the yield of the material, the yield stress of the material. Now, for the second case, where if you apply the equation number 20 for pure shear case, the criteria, yielding criteria von Mises. So, it can be for the pure shear case, what will happen? That means sigma xx and sigma yy and sigma zz would be 0, and therefore, because the pure shear, so sigma xy would be equal to plus minus say the shear, the material of the shearing constant of the material. Say one can then write down plus minus k. So, if where the k is taken as the yield stress in shear, where just like we took the sigma as the yield stress in tension, similarly the k, let us take it as the yield stress in tension shear So if you substitute the value in the yield criteria which was previously in the equation number 20, so one can get K, which is, it would be equal to K1. So that's the K1 is the constant. So since all the stresses except sigma xy are 0 from equation number 23, and quantities which is there in where the K is equal to K1, the relationship between the yield stress in tension and shear can be very well correlated as K is equal to sigma divided by under root 3. So the von Mises yield criteria therefore can be written in this form, which is given in equation number 27, and that comes out to be very simplified manner, that is the function, the yield function would be 1 by 6 and having 4 major elements. The element 1 will have therefore, like in equation 27, sigma xx minus sigma yy square plus second term is sigma yy minus sigma zz square plus third term as sigma zz minus sigma xx square plus the fourth term which will consist as 6 and in bracket sigma xy, the all the shear component, that is sigma xy square plus sigma yz square plus sigma zx square, and this all together and minus sigma square by 3, and that must be equal to 0 because the K from the equation number 27 it comes out to be sigma by root 3, and therefore K square will replace by it will be replaced by sigma square by 3. So this equation number 27 then it can also be written in another form in tensorial manner. So if this function 27 is represented in tensor form, so it becomes f is equal to 1 by 2 and derivative part of the tensor stress tensor Ij and multiplied by again the derivative part of the stress tensor It minus sigma square by 3, and that must be equal to 0. So if you square it out on the both side, then one can also calculate it in the full form of the equation, that is the stress in case of von Mises yield criteria can be written as shown in equation number here equation number 30, like so that becomes 3 by 2 and then we have sigma x derivative part square plus sigma yy derivative square plus sigma zz derivative square plus twice of the shear, all shear component summation of those with the square terms, and then has to be under root because the equation 29 it is square of that, so under root should be there, and then it can further be simplified by taking it out few of the term and rearrange in the form of equation number 31, and therefore one can see it becomes half of and in 4 terms sigma xx minus sigma yy square first term, second term as the sigma yy minus sigma x zz square, and plus third term as sigma zz and sigma xx square plus 6 of the shear component is square of the summation of the square of those shear components, and this is all in under root. The same equation 31 can be further arranged and it can be then simplified because we can write down the x, y and z as the principal direction as 1, 2, 3 as stated earlier also. So this equation 32 it becomes a very simplified manner, and therefore it is half of sigma 1 1 minus sigma 2 2 square plus sigma 2 2 minus sigma 3 3 square plus sigma 3 3 minus sigma 1 1 square under root, and that is the basis of your von Mises yield criteria. Now let us see what is flow rule. So, correlating this yield function, one can see that a flow rule can be devised. So, a general flow rule in fact that would give the plastic stress strain relation can be derived using the concept of the plastic potential. So, what is plastic potential? Say if you go on building the yield stresses. So, a stage would come when this stress potential that we may say as the plastic potential is sufficient to cause yielding. So, this is what the concept of plastic potential can be viewed in. It is based on the in fact a hypothesis that there exists a plastic potential which is in fact a scalar function of the stresses. So, from this plastic potential the plastic strain increment, that is d epsilon ij, the set of all these increments can be obtained by just by differentiating a function which is g sigma ij. So, if you differentiate with respect to the strain increment, one can get this as the which is defined as the plastic potential g sigma ij, and that can be written in the form of equation number 33, where d delta one can see here. So, that means it becomes the equation as the d epsilon ij, which is the increment of the strain tensor, and it becomes deva g sigma ij deva sigma ij and d lambda. As earlier stated, the d lambda is a non-negative constant. The above definition, that is equation number 33, which is of plastic strain increment, is more broad and it is a general and therefore is called as a non-associated flow rule, because d epsilon ij is not associated with the yield function f now, if you recall. In the special case when the g, that is plastic potential function g, becomes equal to the flow function, then it may lead to the association of the flow rule. It can be associated very well. So, the von Mises yield criteria, where we defined the yield function as f, which was previously derived as equation number 27, if you put this into, if it is associated, so it can be replaced with current Mises yield. So, it can be written as deva f and divided by deva sigma xx. So, that would be equal to simply 1 by 6, as earlier we have seen, twice sigma xx minus sigma yy minus twice sigma zz minus sigma xx, and that would be equal to simply 1 by 3 in bracket twice of the sigma xy sigma yz minus sigma zz. So, and that can be further arranged in the form of equation number 34 here, and that can further be compressed with sigma m, and therefore it becomes equal to sigma x minus sigma m, and that is what we have mentioned earlier, the derivative part. From the start was correlated with the hydrostatic part of the curve. So, this and therefore the equation from the earlier equation 33 can now be the strain increment can be now said as d epsilon ij is equal to d lambda and deva f sigma ij divided by deva sigma ij, and therefore one can further arrange this, and that can be put in the form of equation number 35 as d epsilon xx divided by derivative part of the stress xx, and that becomes equal to d lambda. Similarly, one can write it for the YY component and ZZ component as well as. So, if you substitute for an example the value, the derivative part of the stress in XX direction from the equation 35. So, equation 34 that we where the sigma m was introduced in the equation. So, it can be written as d epsilon ZZ g epsilon XX, and that would be equal to 1/3 of within bracket twice of the sigma XX minus sigma YY minus sigma ZZ, and that would be multiplied by further by d lambda, and that can further be written as 2/3 d lambda in bracket sigma XX minus half of the sigma YY plus sigma ZZ, and this equation 37 can be again written for the other counterpart for the incremental strain in YY direction and incremental strain in ZZ direction as well as. So, from the equation previous equations 27 and 33, one can say that deva f, that is a flow function, deva f divided by deva sigma xy, that is the with respect to shear, it would be become as the shear component, as that for the direct part we did. So, the equation, because there is equation number 27 where sigma xy and sigma yz and sigma yz and sigma xy and other thing have been clubbed together as twice of the sigma square xy, twice of the sigma square yz and twice of the sigma square z. Therefore, one can further propose it for the shear component as shown in equation number just and so it can be represented in the form of equation number 38. So, it becomes deva deva epsilon xy divided by stress, that is the shear stress xy, and that would be equal to d lambda. And similarly for the other component can also be written. So, if we associate the flow rule for von Mises, so in general it can be written as in equation number 40. So, it can be then written as d epsilon xx divided by derivative part of the stress xx is equal to d epsilon yy divided by derivative part of the stress in yy direction, and it would be equal to d epsilon zz divided by the derivative part of the stress in zz direction, and similarly it can also be equated with shear component of the stresses, that is it would be equal to d sigma xy divided by sigma xy, and it will be d sigma yz divided by sigma yz, and it would be further equal to the other component, and it would be equal to your d lambda. So, the same thing can be represented in the tensor form, which is in given in equation number 41. That means in the tensor form the strain tensor, increment of the strain tensor would be equal to the stress tensor multiplied by d lambda. So this forms the basis of incremental strain, and then based on these incremental strain, now a generalized stress and generalized strain increment can also be proposed, because it is useful to define a generalized stress, that is sigma bar. If we say it as a sigma bar, which is represented as generalized stress, and similarly a generalized strain, which would be represented strain increment in the, like it can be represented as d epsilon bar, so that the plastic work increment which we computed earlier per unit volume, say it is dW, can be evaluated as, because the multiplication of these two stress, generalized stress multiplied by the generalized strain increment, and therefore it can be written as in the equation number 42 here, that is dW would be equal to sigma ij d epsilon ij in the form of tensor, and that the same thing can be extended this tensor, and it would, if you apply the relationship that we had equation number 40 earlier, so this dW can be written as sigma ij prime, that is the derivative part, multiplied by d epsilon ij, that is the incremental strain tensor, and that would be simply written as sigma bar multiplied by d epsilon bar. So that is the generalized multiplication of generalized stress and strain. It is convenient to define the generalized stress to be equal in magnitude to the yield stress in simple tension. Thus, from the if we look into the von Mises criteria, equation number 27, it can then be further written in this form of the equation 43, which is, now it is generalized stress which can be equal to the sigma, and that would be under root 3 by 2 derivative part of the strain tensor and again derivative part of the strain tensor. So this format of equation 43 is a generalized strain increment, can now be, from this equation can now be calculated very easily from, and then it will be written as d epsilon ij is equal to d lambda and the sigma ij prime, that is the derivative part, or simply it can be written as d epsilon ij d epsilon ij, and it is equal to d lambda square and sigma ij prime sigma ij prime. It can further be separated on the left side as the sigma lambda is d sigma d lambda square, and it would be equal to the numerator as d epsilon ij d epsilon ij, and in the denominator it becomes the derivative part of the strain tensor and again derivative part of the multiplication 2 times. So and that can, if you substitute the value of those things, then it will be coming as 2 by 3 d lambda is equal to under root, numerator part it is 2 by 3 d epsilon ij divided by, in the denominator as 3 by 2 sigma ij prime, that is the, and therefore the incremental work can be written as in equation number 45, that means it is generalized stress multiplied by generalized strain increment, and that can be further written as sigma ij multiplied by d epsilon ij, and that is the derivative part, it can be then replaced because it can be derivative part and the strain increment tensor, and then one can further convert the equation number 41 using that d increment of the strain, generalized strain, can be now put in the form of equation number 46. So it becomes numerator part as sigma ij prime, derivative part sigma ij prime d lambda divided by under root 3 by 2 sigma ij prime sigma ij prime. So this equation, once we substitute the value of d lambda from equation number 44 earlier derived, it can then further be written as the strain increment, generalized strain increment as under root 2 by 3 and strain increment ij and strain increment ij. So from this particular, the previous equation number 43 to this particular equation, one can then say that the d lambda becomes 3 by 2 and generalized strain increment divided by generalized stress. So and then the associated flow rule can be written like here in equation number 49, that is the associated flow rule for one mices can now be written as d epsilon xx divided by sigma xx derivative, and it should be equal to d epsilon yy divided by derivative stress in yy direction, and likewise then the shear strain component associated with the shear stress, and then here the last term one can see it, the whole thing becomes equal to 3 by 2 multiplied by generalized strain increment divided by generalized stress, and that must be equal to d lambda. So this is what the associated flow rule corresponding to von Mises criteria, yield criteria stands. Let us see what is yield surface. Now this criteria can be represented on yield surface. So what is yield surface? So yield surface is one can see an hypothetical surface that lies where it is assumed that the material is going to yield across the surface, and that this yield surface becomes the concept of, if you recall back your necking. So you will see the material, which if the material is brittle, if the material is elastic, it is a very specific cup and cone and the fracture and associated. So one can define those situations with the help of yield surface. So let us start with, so von Mises yield criteria, we have already seen that it gives 3 by 2 derivative part of the stress ij tensor, and again derivative part of these multiplication minus sigma square is equal to 0. This is what the von Mises yield criteria. Okay. So all of you should remember that this particular equation, if you do it for the only direct stress, can be written as sigma 11 square plus sigma 22 square plus sigma 33 square derivative, all derivative part, and that would be simply equal to under root 2 by 3 sigma whole square. This is an equation, you can see it is a square term on the left and the other, so it radius. So what does it represent? Anybody can guess here? Yeah, yes, Manish? Yeah, that's correct. So it represents a equation of a sphere that has a radius under root 2 by 3 sigma, and the principal in the principal Dievateric stress space, that is sigma 1 prime, sigma 2 prime and sigma 3 prime. So let us consider this one Mises yield surface, which is a spherical yield surface in the principal stress coordinate system, and let the principal stresses at a point as shown in figure number 6 here, where the principal stresses at a point P in the stress space has been shown here, one can see. So if the P lies in the stress space of sigma 11, sigma 22, sigma 33, then one can say that OP1 is equal to sigma 11, OP2 is equal to sigma 22, and similarly the OP3 would be equal to sigma 33. Now let us consider the line OH, which is equally inclined to each of the axes, 3 axes as shown here in the figure. So its direction cosine, if you calculate, so it comes out to be, because it is equally inclined with all the axes, and therefore its direction cosine would be 1 by root 3, 1 by root 3, 1 by root 3, which we previously defined as L, M and N. So the projection ON of OP on OH can be now found out. So that becomes ON as sigma 11 by root 3 plus sigma 22 by root 3 plus sigma 33 by root 3, and therefore the Pn square can be written as summation in a bracket sigma 11 dievateric, sigma 22 dievateric, sigma 33 dievateric minus 1 by third in bracket sigma 11 sigma 22 sigma 33 square. And if you simplify this equation, Pn square on the left side and right side these terms, so that this can be further arranged and it becomes in the format of equation number 51 as 1 by 3 sigma 11 minus sigma 22 square plus sigma 22 minus sigma 33 square plus sigma 33 minus sigma 11 square. So this equation number 51, let us see here again to that this line which is H, which is equally inclined with all the axes. So this particular, if you recall the equation number 32 earlier, then one can write down the Pn square in this form, which is Pn square is equal to 1 by third sigma 11 minus sigma 22 square plus sigma 22 minus sigma 33 square plus sigma 33 minus sigma 11 square, and that should be equal to 2 by 3 sigma square, and that is how the Pn becomes under root 2 by 3 sigma. So this yield locus, it gives a yield locus, and that locus is what? It's a circle having a radius under root 2 by 3 sigma. That means it follows that von Mises yield criteria in principle stress space, if it is replaced by a cylinder having a radius under root 2 3 sigma, whose axis is the line which is through the origin and which is inclined equally with the coordinate axis, which is now shown here in equation number 52 and the figure 7. It states where the states of the stress, which now can be plotted as a point within the cylindrical represent material in elastic state. So the hydrostatic stress does not affect yielding, one can see here. Hence the value of On, which is from the previous equation number 5, has no effect on yielding. Therefore the intersection of the this particular yield cylinder with any plane which is perpendicular to its axis will be therefore a circle. So one can see here that this represents a hexagonal cylinder, and inside and outside represents your circular cylinder corresponding to van Mises, and this is the axis of cylinder which is equally inclined. So this is what a pi plane. So the pi plane is a plane which is perpendicular to the axis of yield surface and which passes through the origin. Its equation is therefore sigma 11 plus sigma 22 plus sigma 33 is equal to 0, and therefore it is a deviatoric plane. That is true. On the pi plane, therefore the positive principal axis, that is if we see the O sigma 11, O sigma 22, O sigma 33 from the center appear in which is to be inclined at 120 degree to each other, which is shown here in equation in figure number 8, and when negative axis of the principal stress are included, the whole area of plane gets divided into 6 equal sectors as shown in figure number 8. The coordinates of the point P appears therefore here as shown here. If you project it on the point P on the pi plane, and therefore the projected length, that is OP dash, if you see here, if it is can be calculated as under root 2 by 3 sigma 22 and P2 dash H2 dash from the figure, that becomes 2 by 3 under root sigma 233, and similarly the H dash P dash becomes the under root 2 by 3 sigma 11. If the Cartesian coordinate of the point P dash, if it is taken with respect to OB and OD axis, if say it is the coordinate is xy, then one can now find out x, and in as shown in equation number 53. So x becomes under root 2 by 3 sigma 22 prime cos 30 and minus 2 by 3 under root sigma 11 prime cos 30, and that is nothing but sigma 22 minus sigma 1 by root 2. And similarly y can also be calculated as shown in here in 54, equation number 54. And therefore if you see these two, if you calculate from the equation number 53 and 54, so the r square it would be equal to the x square plus y square, and then it can be calculated here, because the cos square and sin square it can be separated out, and therefore r becomes as shown in equation number 55 as 1 under root 1 by 3, and the whole set of 3 terms like sigma 11 minus sigma 22 square plus sigma 22 minus sigma 33 square plus sigma 33 minus sigma 11 square, that is the radius. And therefore one can see the position if it is projected as shown in figure 8 explained earlier, and it is projected the point P when it is projected on the pi plane here. So if you plot like this sector wise, if you plot it like sector wise, so one can find out the van Mises criteria on the pi plane here, as here in equation in figure number 9. So one can see that this is the line of pure shear, and B, C, D, A dash, C, D dash and A corresponds to the different sectors. So one can see here that if you see the B, C and D sector, which is between, so between the sector BC, so we have 1, 2, 3 and there are 12 sectors. So if you take the sector BC where sigma 22 is greater than sigma 33 and it is either equal to sigma 11, that is the sigma 33 lies between sigma 22 and sigma 11, and likewise all the sectors has got, and one can draw this von Mises circle, and it is a, that means that cylinder on XYZ principal stress, when it is transferred to the pi plane, it would look like a circle, and this circle one can see here the different regions, and then one can find out the value of theta, which is mentioned here in equation figure number 8, that is which is projected on the pi plane, the angle which is projected on the pi plane, one can then calculate using equation number 56 here. So that is simply theta is equal to tan inverse y by x, and if you substitute the value of y by x as previously calculated, so one can find out the value as tan inverse this whole set as shown in equation number 56. So using the von Mises yield criteria as in 32, the equation, this particular equation 55 can be written as R is equal to, where the radius of the circle is under root 2 by 3 sigma. The von Mises yield locus therefore is a circle which has got a radius equal to under root 2 by 3 sigma, and it is again shown at here on the for the plane stress. If you plot it the plane stress, so the third stress is 0, so the sigma 22 is 0. So if the same thing if you draw it for the plane stress condition, so now you have the same sectors look like as an ellipse. You can substitute in the equation, previous equation, and if you substitute you will get an equation of an ellipse. So here the important is here that the sectors turns into an ellipse here. So what we see that for the plane stress where it is in 2 dimension and this will yield a rectangular axis coordinate axis sigma 11 and sigma 33, and the equation, the yield criteria equation, von Mises yield criteria equation would reduce to equation as shown in equation 58, that is sigma 11 square plus sigma 33 square minus sigma 11 sigma 33, and it is equal to sigma square. And this also shows an ellipse having the major axis as 2 under root 2 sigma and the minor axis as 2 under root 2 by 3 sigma, and the ellipse is perpendicular, which is bisecting, bisectors of the angle between sigma 1 and sigma 33 has been shown here in equation figure number 10. So this is what we have seen, the von Mises yield criteria on pi plane, and then when it is drawn corresponding to plane stress condition where the sigma 22 is 0, then it looks like an ellipse. So another important yield criteria is Tresca, the Tresca has been another very popular scientist long back around 1864, who discovered experimentally as well as that the plastic deformation starts when the maximum shear stress. This is the Tresca yield criteria is also mentioned as the maximum shear stress theory. So what he mentioned that the plastic deformation occurs when the maximum shear stress reduces the value of yield stress in pure shear. So that is the pure shear theory, maximum shear stress reaches. So based on this, the Tresca proposed a simple, very simple yield criteria, which is shown, which can be represented, written in the form of equation number 59. So the flow function can be written as F is equal to sigma max minus sigma minimum, and that is equal to constant. So here sigma max and sigma minimum are algebraically largest and smallest principal stresses out of the three stresses given respectively. So if the principal stress say are sigma 1, sigma 2 and sigma 3, which satisfy the inequalities like sigma 1 is greater than or equal to sigma 2 and that is also greater than or equal to sigma 3, that is the sigma 1 is the greatest of all the three stress field. So the yield function, this yield function as shown here in 59 can be written it as F is equal to sigma 11 minus sigma 33 and minus the constant value. So what will happen in the pure shear if you apply it? So for the pure shear it would be simply sigma 11 would be equal to minus sigma 33 and that would be the shear stress of the material, because sigma 22 is 0 here. So that gives a constant which is equal to 2K, and if you apply it for the simple tension where sigma 33 is 0, sigma 22 is also 0. So sigma 11 would be equal to the tensile stress of the material sigma, and that would be a constant equal to the sigma therefore, and therefore the yield criteria can be written as sigma 11 minus sigma 33 is equal to twice K or equal to twice K corresponding to the shear, pure shear, and if it is unidirectional tension then it is equal to sigma. So out of this equation number 61, then one can say that the tensile stress is equal to 2 times of the shear stress of the material, and the von Mises, whereas if you recall back the von Mises criteria, this tensile stress was calculated at under root 3K, that was given in equation number 27 if you recall. So this criteria, that is Tresca criteria, is obviously less complicated if you see mathematically, if you compare with the von Mises. So the criteria however does not take the intermediate stress into consideration and requires the knowledge of maximum and minimum principal stresses in has to be taken. So that is the difference. So if we look into the concept of plastic potential again, so the where you have a function plastic potential G sigma ij, and the increment of the strain increment, and it was correlated with d lambda. So the flow rule for Tresca yield criteria can now be generated. So if you recall the function, that the plastic potential function equation, so the Tresca criteria that would be simply written as which is f is equal to sigma 1 1 minus sigma 3 is equal to twice k, where the sigma 1 is the highest, and therefore it can be written as deva g sigma ij divided by deva sigma ij, and this can be evaluated by replacing g with function f, which is your Tresca function, and therefore it can be written as in equation number 63 as d deva f divided by deva sigma 1 1, and it is equal to 1, and therefore deva f deva similarly sigma 2 2 would be 0, and deva f by deva sigma 3 3 would be equal to minus 1, and therefore one can say that the strain increment in 1 1 direction is equal to d lambda. Similarly, strain increment in and because the two sigma d epsilon 2 2 is 0, and therefore d epsilon 3 3 can be evaluated as minus d lambda, which is shown here in equation 64, or simply it can also be written as d epsilon 1 1 is equal to minus d epsilon 3 3. And therefore now based on these, for the Tresca criteria similarly, the generalized stress and generalized strain increment can be proposed in the incremental plastic work form. And if you recall back, just like we did it for case of von Mises, one can then write down the incremental work done, that is the plastic work done, which would be equal to sigma ij tensor, and multiplied by the incremental strain tensor, and that can be further written as generalized stress multiplied by generalized strain increment, and that can be further expanded as shown in here in 66, equation number 66. So that is the three terms corresponding to 1 1, 2 2 and 3 3 directions, and therefore the Tresca flow rule now if you apply corresponding to equation number 64, so one can find out dW, that is the incremental work done, would be equal to simply sigma 1 1 minus sigma 3 3 d lambda, and if we set the generalized stress which is equal to sigma, and that is nothing but sigma 1 1 minus sigma 3 3, the generalized stress increment, that is d epsilon rho can be prime can be obtained as d epsilon generalized strain increment, which is equal to d lambda, and that is equal to strain increment in 1 1 direction, because if you recall earlier equation number 65, so that becomes your equation number 69 here. So we would continue further the final equation like we derived it for, so we would further continue. So I would like to thank you once again for your patience, and in the next lecture these two criteria we would see on the experimental basis where it stands. Both the criteria are good, but if you recall the figure number 8, 9 and 10, where the yield criteria it was also drawn for the Tresca, that because Tresca we did not started by the time, so I did not mention there, but it was drawn there also. So you will see on the even the pi plane, the cylinder, that is the round cylinder, corresponds to the von Mises, and the hexagonal cylinder, likewise the circle, complete circle, corresponds to the von Mises, and the hexagonal polygon corresponds to the Tresca. And on the pi plane, similarly, the ellipse, which is the ellipse, and it is a hexagonal ellipse form. So we would verify experimentally, people have already verified it, and right now I can say the von Mises is much more popular, and we would be looking into the experimental on the basis of experimental verification next time. Thank you once again to all of you for keeping patience during the lecture, and please do not forget to give your feedback so that I can improve further. Thank you.